All right, hello and welcome. We live in a world that moves at digital speed, right? But our health crises, man, they often move even faster. So today we're going to dive into something pretty incredible, a new approach that's helping science not just catch up, but actually get ahead. We're talking about creating vaccines at the speed of code. So, how do you fight a pandemic that moves faster than science? I mean, this question, it hits pretty close to home for all of us, doesn't it? We all just live through that frantic race. When a new virus shows up, every single day, every hour, it counts. And the way we used to develop vaccines, well, it was reliable, but just painfully slow. So what if, and this is a big what if you could just change the rules of the race entirely? Well, that's exactly what's happening right now. We are entering an era where vaccine development is going through this radical transformation. And it's all thanks to a powerful new tool that doesn't start in a lab with test tubes and beakers, but on a computer with lines of code. So the key to all of this is something called in-silico vaccine design. And the name itself is pretty cool, right? In-silico, it comes from the silicon in computer chips. The best way to think about it is like this. Imagine you're designing a new car. Instead of building thousands of real physical prototypes, what if you could first build a perfect digital blueprint? You could test it in a simulation, check its safety, see how it performs, and only then build the real thing. Well, that's exactly what we're now doing for vaccines. Okay, so how does this actually work in practice? Well, it's a pretty fascinating four-step process. First up, scientists take the virus's genetic code, its instruction manual, and feed it into the computer. Then, powerful algorithms get to work, and they predict the virus's weak spots. You can think of these like the Achilles heel of the virus. They're these specific little parts, called epitopes, that our immune system is really good at latching onto. Step 3, they simulate a full-on immune attack in the virtual world to see which targets work best. And finally, with all that data, they design the perfect digital blueprint for the most promising vaccine, which is then ready for real-world testing. Now, this digital-first approach, you've got to understand, this isn't just some minor tweak to the old system. No, this is a complete game changer. The advantages are just enormous, and they're fundamentally changing how we race against disease. And when you look at the comparison, the difference is, well, it's staggering. Think about it. Traditional development is this long, slow marathon of physical trial and error. It can take years and cost an absolute fortune. In silico design, it turns that marathon into a sprint. Because you're doing all that initial work on a computer, you can slash the timeline from years down to months, sometimes even weeks. The amount of time and money saved is just incredible. And look, the benefits go way beyond just speed and cost. For one, you get this incredible precision. We can design vaccines that are potentially way safer and more effective right from the get-go. Then there's flexibility. When a new variant of a virus pops up, we can adapt the design incredibly fast. And finally, the application is just so wide. These same tools can be used to fight everything from the next big pandemic to those neglected diseases that affect millions but don't always grab headlines. Okay, so I know what you might be thinking. This all sounds fantastic in theory, but is it actually happening? Is this real? And the answer is absolutely. So let's take a look at how this technology is moving from the computer screen into the clinic to tackle some of the deadliest viruses on the planet. And yeah, to be clear, we're not talking about science fiction here. Let's go to India, where researchers are on the front lines, using in silico design right now as a primary weapon against some really severe viral threats. Take, for example, the Nipah virus. This thing causes outbreaks with terrifyingly high fatality rates in places like Kerala. Using these computational tools, researchers designed what's called a multi-epitope vaccine. It's super smart. It's designed to target several of the virus's weak spots all at once for a more powerful punch. Then you have KFDV, this nasty tick-borne hemorrhagic fever. The existing vaccine for it only gives you short-term protection, but now they've designed a new subunit vaccine, which basically just uses a tiny, harmless piece of the virus to train your immune system, and it's showing incredible promise for much stronger, much longer-lasting immunity. And it's really important to see that this isn't just a few scientists working on isolated projects. No, this is a coordinated national strategy. This quote really says it all. Institutes like IBRI are using this tack to speed up discovery, cut down on time and cost, and make the whole process way more precise. They're basically building these powerful hubs to fight diseases that are a threat not just to India, but to the whole world. So let's zoom out for a second, because this technological leap, it's not just changing what happens inside a lab. it is changing our entire approach to global health. And as you might guess, it's also creating this whole new frontier of jobs and career opportunities. Yeah, this technology is a perfect example of a really crucial idea called One Health. It's pretty simple, really. It's the understanding that the health of people, the health of animals, and the health of our environment are all connected. You can't separate them. And since most new infectious diseases actually jump from animals to humans, we desperately need tools that can work across that boundary. Well, in-silico design is literally perfect for this because it lets us quickly analyze and prepare for these threats before they explode into a crisis. And of course, this revolution is creating some incredible new career paths. I mean, think about it. We need a whole new generation of scientists, people like computational biologists who can literally write the code for immunity. We need immunoinformatics scientists who can model the entire battle between a virus and the immune system. We need epidemiologists who know how to use these digital tools to protect whole populations. This is where biology meets big data, and honestly, it's one of the most exciting and important fields you could possibly get into right now. So when you see just how fast this technology is moving and the incredible impact it's already having, it all leads to one final, really fascinating thought about what's coming next for medicine. So I'll just leave you with this powerful question to think about. Is it possible that the next major medical breakthrough, the cure, the vaccine that saves millions of lives, is it possible it's not waiting to be discovered in a petri dish? Maybe it's already sitting on a computer somewhere, assembled, tested, and perfected as lines of code, just waiting for someone to hit run. Thanks so much for joining me.